Please download the latest programs.v file from Canvas, because you have to just continue with me as I go along here. So the last thing we saw in the last session was how to optimize basically syntactically, how to make simple syntactic optimizations where we took an arithmetic expression, and whenever we had 0 plus something in it, we just removed the 0. Okay. Today, we're going to go a little bit deeper. And first, I'm going to start with a very simple thing that you can do in Coq, and that's defining new tactics. So let's say that I want to prove this theorem. Now, it's a very simple theorem. It says that if the list AB is equal to AC, then B is equal to C. Now, I can prove it in the normal way. I can say do intros and then do injection on H and do intros again, and then suddenly you have it as an assumption. Now, here's how you can actually define your own tactics. You use the word LTAC. So you write LTAC, and then you give the name of your tactic. I'm going to call it my tactic. And then you say what parameters it takes. It takes H here. And I'm just going to say, whenever I write my tactic H, what that means is try injection H intros assumption. And then I can use this tactic when I'm proving lemmas. So for example, I'm proving this lemma and I just say intros, and then I say my tactic H. Okay. So this is again useful if you want to use the same idea, the same proof idea over and over again. You can just define it as a tactic and just apply it whenever you want. Now, another thing that is quite useful is a tactic called LIA. And this one basically does Pressburger arithmetic. So let me show you the Wikipedia page for this. So this is the Pressburger arithmetic. And basically, it's an arithmetic that has natural numbers. It has all the logical operators that you expect. It has 0, 1, on successor of 1, and so on. And it also has addition and checking for equality. It also has like other types of comparisons, less than or equal, and so on. But the really important point here is that we don't have multiplication. So we only have addition. And actually, Pressburger arithmetic is known to be decidable. And because of that, Coq has this tactic called LIA, which basically solves anything that can be written in Pressburger arithmetic. So here's an example. Let's say I have 4 variables, M and OP, and this is what I want to prove. I want to prove that M plus N is less than or equal to N plus O, and O plus 3 is equal to P plus 3, implies that M is less than or equal to P. So the really important point here is that I don't really have multiplication. I can have multiplication by a constant. That's fine, because multiplication by a constant is just a series of additions. But I don't have multiplication of 2 variables. And whenever you have terms that look like this, you can just do intros and then apply LIA. And Coq can solve those things automatically.
Comparisons in that Pressburger?
Yes, you can also have comparisons. You have equality, not equality, less than equal, greater than equal. You have all of this.
That comes because of if you want to make it equal or not, you just subtract and just say it's smaller than 0.
Yes. Basically, with negation, you can create everything. So here's another example. I want to say that addition is commutative. A very simple proof that I can give is that I can just say apply LIA. This one says that addition is associated, and the proof is again just LIA. Now, the next thing I want to show you is that we can actually define propositions inductively. And if you think about induction, generally speaking, we want to show that a particular proposition holds for, let's say, all natural numbers, right? And then we show that it holds for 0, and if it holds for a natural number n, it will hold for n plus 1. But we can use this kind of inductive thinking to do the definition itself. So I can, for example, define something called something called EV, which takes a natural number and returns a proposition. And basically, EV is supposed to say whether the natural number was even, okay? So now the way I do this is that I just write the rules for a natural number to be even. So you should think of this as a rule-based definition. So the first rule is called EV0. And what it says is EV0, 0 is even. Okay, so this is a proposition that says 0 is even. And the second rule, I call it EVSS. It takes a natural number n, and it says that if n is even, then n plus 2 is also even. So S of n is even. Okay. So this is now an inductive proposition. And just look at the way that we define this. We say that it maps natural numbers to propositions, because for every natural number I have a particular proposition EVI. And then this part here is telling me what are the rules to make sure that a particular proposition holds. So I can always assume that EV0 holds. And if EVN holds, I can say EV of S of n holds. So now I can use this to prove a theorem. So let's say I want to prove that 4 is even. I say I have a theorem, EV4. And by the way, this is very different from the previous even function that we had, because previously we had a function that took a natural number and returned a Boolean. But this is not a Boolean, this is a proposition. Okay. So I want to prove that 4 is even. What can I do? I start my proof. I first assert that 0 is even. Now I have to prove this. I say, okay, just apply the rule EV0. So these are rules now. And I just apply the rule EV0 and I get that 0 is even. Now I assert that if 0 is even, then 2 is even. And how do I prove this? I say apply EVSS with n equal to 0. Okay. Now I know that 0 is even, and if 0 is even, then 2 is even. So I want to get that 2 is even. So I just say apply H0 in H. Now I get that 2 is even. Now I just continue this for another step. So I just say, let's just assert that evenness of 2 implies evenness of 4. And then again, it's the exact same thing as before. I apply the EVSS rule. And then I do a rewrite, and now I have EV of 4 in my assumption, and that's what I wanted to prove. So great. Okay. Here's another way of doing exactly the same thing. So this is my proof. I just say repeatedly apply EVSS until you can apply EV0. So I apply EVSS, and then for every subgoal, apply EV0. And you see that this one immediately solves this. We've talked about semicolon in the past session. It's exactly the same thing. Okay. Here's another way of writing the same inductive proposition EV. So previously, let's look at this definition. I said that my first rule is that EV0 holds. But my second rule was that if EVN holds, then EV of S of n also holds. But if you think about this, if you think about it in terms of rules, this is also an assumption, right? So I have the assumption that n is a natural number. And then I have the assumption that EVN. And then my rule gives me EV S of n. So I can write the assumptions as parameters basically here, as if they're parameters. So I can write it like this. I can say that my first rule, I'm calling this one EV prime, is that EV prime of 0 holds. And my second rule, which is called EV prime SS, says that if n is a natural number, and if I have this assumption H, which says n is even, then I have EV prime of S of n. So n plus 2 is also even. Great. And also you can check the type of EV prime, and you see that the type is actually this proposition. I just wanted to give it a name. You can, I'm using H because it's a hypothesis, but you can give it whatever name you want. Okay, and then again, I can apply that, I can prove that with this new definition of EV prime of 4 holds as well, and again, same thing as before. But again, the very important point about these inductive definitions is that basically what I'm saying here is that I'm giving you some rules for when EV holds. And I'm saying that EV of some number I holds if and only if you can deduce it from these rules. Okay? So it's an if and only if. These are the only rules that you have. Okay. Now let's do something else. Let's say that I want to somehow model Collatze's conjecture, and we'll see what we're going to do. So let's say I define a function called div2, which basically divides by 2. It's a very simple function. If it's 0, returns 0. If it's 1, again, returns 0. And if n is basically in this format, s of n, it just, maybe it's better if I call it n prime. So if n is n prime plus 2, it first divides n prime by 2 and then adds 1 to it. Okay. So here's a function that should be kind of familiar to you. I define the function f on a natural number n, and I say if n is even, then divide it by 2. Otherwise, compute 3 times n plus 1. Okay, so I call this f. Now, if I do this, I can now basically write Collatze's formula, which said that you start with any given number. If it's even, you divide by 2. If it's odd, you multiply it by 3 and add 1. And then you just repeat the same process. Now, Collatze's conjecture is that you will eventually reach the number 1. Okay? So I can write something like this. I can write a function which basically counts how many steps it takes to reach 1 if I start from n. Okay? So I say if n is already 1, then it takes 0 steps. Otherwise, the number of steps is 1 plus the number of steps that it would take starting from f of n. Okay, so I'm defining a recursive function. Yes, great point. We don't know if this terminates or not. And actually, if you can prove that it terminates, you have proven the conjecture, right? But the thing is, in a lot of programming languages, you can actually write this function. So you can write this function, let's say in C++, right? And the compiler would accept it and it would actually run it. Not here. So every function in Coq should always terminate, and every function in Coq should always return something. You cannot have partial functions. Okay? Now, here's what happens. Look at this. It says the recursive definition of this function is informed. And yeah, so basically, when you're doing fixed points, you're kind of doing an inductive definition. And again, all inductions in Coq are structural inductions. So when you take n and you have a recursive function that works on n, you can recursively call it on something that is smaller than n, which means that you look at the constructor of n and you take the things that are in there. But you cannot call it on something that is bigger than n, like f of n. So in this case, it just says you can't do it. I add the keyword fail to just say, forget about this. But here's the thing. I cannot define it as a function. I can define it as an inductive proposition, right? So I can define a proposition reaches 1, which basically says for every natural number, does it reach 1 or not? Okay. And here's the inductive definition that I have for it. My first rule, which I call term done, says that if you start at 1, you reach 1. So reaches 1 of 1 holds. My next term, my next rule, which is called term more, says that if n is a natural number, and if from f of n we can reach 1, then from n we can also reach 1. And now this definition works. Why does this definition work and not the previous one? because the previous one was supposed to be a function, and Coq was supposed to be able to compute with it. So if you give it some number, it was going to try to compute the value of the function at that number, right? So in those cases, it has to terminate, and you couldn't really show Coq that that function terminated, so Coq didn't accept it. But here, you're just defining proof rules. You're saying, this is how I can prove that reaches 1 holds for a particular number. So this is the difference between inductive propositions and functions, recursive functions. And now, actually, I can even use my inductive proposition inside a theorem or conjecture or so on. And actually, when you write conjecture, Coq doesn't ask you to prove it. It's just like you're noting it for yourself, giving it a name. If I had written it as a theorem instead of a conjecture, then you see that I have a goal that I have to prove. But anyway, I can just have a theorem like Collat's conjecture, which says that for all natural numbers n reaches 1 n. I'm going to keep it as a conjecture. Okay. I'm defining a module here because I want to define something that is already in the standard library and I don't want to create clashes. So one of the things that we are very used to when we're working with natural numbers is to compare them. So to have a less than or equal comparison. And actually, this is how you can define that. This is now an inductive proposition that is defining a relation, the less than or equal relation. And what this says, you know how to read this now. It says that you take 2 natural numbers and give a proposition. Okay. So 2 rules. The first rule, which is called LE_n, says that if n is a natural number, then n is less than or equal to itself. So LE of n holds. The second rule says that if n and m are natural numbers and I have LE of nm, then I also have LE of n and m plus 1. So that's how we define less than or equal. We can even go forward with this, and we can define our inductive propositions in a way that is both higher order and polymorphic. You can combine all of these different abilities of the language. So let's say that I want to define the transitive closure of a particular relation R. So let's say I have a relation R, and I also have an implicit type X, and R is a relation between elements of type X. So it's of this format. It takes 2 elements of type X and gives a proposition. Okay. And now let's say that I want to have the transitive closure of R. So if you think of R as edges in a graph, I want to put an edge from U to V if there is a path from U to V in R. Okay. So again, I have 2 rules. The first rule is called the step rule. I say that for any x and y, if R of x, y already holds, then transitive closure R of x and y also holds. Okay. The second rule says that for every x, y, and z, if I have R of x, y and R of y, z, then, if I have transitive closure R of x, y, so if I have, let's say, in the graph representation, a path from x to y, and if I have a transitive closure of y to z, then I also have in the transitive closure of R, x to z. Okay, great. Now let's prove a theorem. This is what I want to prove. I want to prove that for all natural numbers n, if n is even, then either n is 0 or there exists some n prime such that n is basically n prime plus 2 and n prime is even. Okay. Now, I'm not going to give you time to prove this. Let's do intros. Here's the part where things get really interesting. Look at this hypothesis H here. It just says n is even. But I can actually destruct H. Why can I do that? Because the definition of even said that you can prove something is even using these two rules and only using these two rules. So if I have the assumption that n is even, one of these two should have held. Otherwise, n would not be even. So I can say destruct it. I can say do a casework. And that's exactly what I do. So I destruct. The first case is when the first rule holds. And remember, the first rule was that n is 0. And in this case, as you see, this on the left-hand side, I have to prove 0 is equal to 0. So I can just do left and then reflexivity. The second case says that I have some number m, and this m is even. I have this assumption. Okay. And what do I want to prove? I want to prove that either m plus 2 is 0, which is impossible. So I'm going to prove the right side here, not the left side. And I'm going to, in the right side, I'm going to prove that there is some n prime such that s of m is equal to s of n prime, and n prime is even. Okay. So I just have to put m for n prime itself. It's very obvious. So I just do the right-hand side, and then for resolving the existential, I say exists m, and then the rest of it is just basic things. So here's another thing we can prove. Let's say I have a natural number n. I want to prove that if n plus 2 is even, then n is also even. So I do intros. Now I can apply this previous theorem. This previous theorem, which I actually called the inversion theorem for EV, said that if EV of n holds, then either n is 0 or there is an n prime. So I just apply it to H, because here I say that EV of something holds. So I just replace this for n in EV inversion. And so I say apply EV inversion H. And this is what I get. I get that either s of n is 0 or exists an n prime with these conditions. So I can destruct it. Now, in this first one, I can just say discriminate, because it's impossible to have something like this. Now, here, I want to say that there exists some natural number n prime such that n plus 2 is equal to n prime plus 2, and n prime is even. Okay, so I destruct it. I get these things. Again, I have an and here. I destruct again. Now, here's the part where things get interesting. I can actually do injection on H and remove the S. And I do that, and you see that I get n equals to x. I do this. So I know that n is equal to x. I know that x is even. I need to show that n is even. It's just a simple rewrite, and then I have it as my assumption. Okay. But everything that we did right now is also a tactic. So there is a tactic called inversion. Now, how does inversion work? Let's look at this example. Let's say that I want to prove that for all natural numbers a and b, if a plus 1 is equal to b plus 1, then a is equal to b. I do intros first. And now I have this assumption H. Now, so H is in my context. I know that H holds. So if there is anything else that is a necessary condition for H, then I can assume that that thing also holds. Okay? And this is what inversion does. So what is a necessary condition for S of A to be equal to S of B? By definition of S, it's that A is equal to B. So if I do inversion on H, I immediately get A equals B. And then I can do reflexivity. Okay, let's look at this theorem again. We want to prove that for every natural number n, if n plus 2 is even, then n is even. Okay, so I do intros. Now I have this E here, which basically says S of n is even. Now I say do inversion on E. So find the necessary conditions for E. What is the necessary condition for E? In order to have EV S of n, by definition of EV, the only rule that can possibly apply is the rule that assumed that I had EV of n. So if I just write inversion E, I get EV of n here as well. And then I just say it's assumption, and that's it. Okay, here's another proof. Let's say that I want to prove that 1 is not even. So EV of 1 does not hold. Because until now, we were just proving that something does hold. Now I want to say that it doesn't hold. So I do intros. Okay. And look what happens. Why is this going on? So what am I doing here? What I want to prove is the negation of some proposition. I want to prove the negation of EV1. So what does it mean to do intros on this? Look at it. It basically says that I assume EV1, and now you have to get a contradiction. You have to prove false. So this is proof by contradiction now. Okay. So I wanted to have negation of EV1. I do intros H. So I add EV1 to my context, but then my goal is false. So I'm doing proof by contradiction. Let's say that I apply this inversion that I had to H. This is what I get. I say, okay, destruct it. The first case is that 1 is equal to 0. Of course, it's not. So I can do discriminate there. Now, the second case, it says my assumption is that there is some n prime such that 1 is n prime plus 2. Again, that's also impossible. So we have to get it to a contradiction here. So I say destruct it, and I say destruct one more time, and then I say discriminate on H, because discriminate actually understands that this one starts with only one S, but this one starts with two S's. And that's it. So this is how you do proof by contradiction. Here's another way that I can prove that 1 is not even. This is even easier. I do my proof by contradiction, and I just say inversion H. Now, why did this just end the proof? Because I'm telling it to find the rules that can be applied to prove that 1 is even. And it immediately figured out that none of the rules can be applied, no matter what the assumptions are. So as soon as I do inversion of H, this is already done. Okay, here's another trivial theorem. If 5 is even, then 2 plus 2 is equal to 1. Okay, so I do intros, and then I do inversion on H. Now, if I do inversion on H, you see that I get a bunch of assumptions that I have to prove, and one of them is that 3 is even, because it figured out that the only rule that can be applied to prove that 5 is even requires 3 to be even. But I do the same thing again, this time on H1, so I say do inversion of H1. Now it says you should prove that 1 is even, basically. So, sorry, you have the assumption that 1 is even. So, okay, sorry, why did this work? My initial assumption was that 5 is even. I'm doing inversion H, and it says you can additionally assume that 3 is even, because the only way that 5 can be even, according to your rules, is if 3 is also even. So you get this assumption for free. And then I do the same thing with H1, and I get the assumption that 1 is even. But I know that 1 is not even. I've already proven that in the previous theorem. And I just do the same proof here, and that's it. Okay. Here's another way we can use inversion. We can also use inversion with our definition of list, let's say. So here's what I want to prove. I want to prove that if the list NM is equal to the list OO, then N is equal to M. The list N is equal to the list M. So I just do inversion on H. And this is what I get. I get that N is equal to O and M is also equal to O. And it also rewrites this part in the goal. So my goal is now just to prove that O is equal to O. And I say this is reflexivity. Okay, try this one. It's actually quite easy. Prove that for all natural numbers n, if n plus 1 is 0, then 2 plus 2 is 5. Okay, let's do this. Let's start with intros. And you already see that you can just do discriminate h, right? But instead of that, you can also do inversion h. And this works as well. This is another way of just defining the less than equal. I already talked about this, that basically you can put your assumptions here instead of saying that you have an implication. You can just put the hypothesis here. And by the way, this is, of course, how you define notation. We don't spend too much time on how to define notation in this course. You can just look up the Koch manual for that. It's just too much detail that we don't need. And you can then define less than. So you can define that n is less than m when n plus 1 is less than or equal to m. Okay, and then you can define this notation. Okay. So let's do something fun. Let's define regular expressions. So what is a regular expression? A regular expression, you know that you should first have an alphabet, and then you can define the regular expression on top of that alphabet. And the operations that you have is that you can have the empty set, you can have the empty string, you can concatenate, you can take the union, all these nice things. You can take the cleany star, and so on. So I show my characters with a type T. So I say that my regular expression is on a particular type T, and just think of T as my alphabet. Okay. Now, what does a regular expression have? Again, I can have these constructors. I can have the empty set, which is, of course, the empty set. I can have the empty string, which is the set that has only one string in it, and that's the empty string. I can have any given character. So I call that char, and then I take a character from my alphabet. I can have append, which says that if I have two regular expressions, R1 and R2, I can append them together, right? I have union or plus, like I can have R1 plus R2. And then I have the cleany star, which is like the repetition. I can have star of R if R is a regular expression. And of course, in all of these, I want the type T or my alphabet to just be implicit. So I'm going to show you a new way of defining notation. Again, I'm not going to talk too much about notation, but here's the thing. Normally, you first define a function or normally you define a function or relation, and then you define a notation. And you say that when I write this notation, I mean this function. But what happens if your function has, let's say, a very long name, and the function itself is recursive? Maybe I want to use the notation in the definition of the function so that it's more human readable. So this is what we're going to do here. And the way it works is that you have to first reserve your notation. You say that there's going to be a notation that looks like this. And then you define it. Okay? So here's how it works. I say I have a reserved notation S equals tilde RE. And what I mean by this is that, let's say S is a string. So let's say S is a list of type T. And I want to say whether this string is in the language defined by this particular regular expression. Okay. But at this point, I haven't defined a function for that yet. I'm going to define that function later. This is called expmatch. It's actually not a function, it's a recursive proposition, sorry, an inductive proposition. But here's what I do. I say I reserve this notation, and then I write the inductive definition, and inside the inductive definition, I can use this notation. Okay? But then at the end of it, I say where this notation means this, means basically recursive. So that's how I do notation definition. Okay, but forgetting about notation, how do you actually check? So I have this match function, which basically takes a list, or okay, let's not think of it as a function. Let's actually think of it as an inductive proposition. So it's an inductive proposition that takes a list of type T, which means it takes a string, and it also takes a regular expression over the same alphabet T, and it tells me whether that string satisfies the regular expression. Okay, so now again, I just have a bunch of rules. So if you remember our very first theoretical sessions, we had this concept of rules. This is exactly the same thing. I have a bunch of rules that tells me when a particular string satisfies a particular regular expression. Okay, so the first rule is that the empty string satisfies the regular expression empty str. Okay. The second rule, and by the way, every rule has a name. These are the names of the rules. Okay. It can also have a bunch of parameters, and then this is like the result of the rule. The second rule says that the string that has just one character x satisfies this regular expression, char x. Okay. Now, this one is a little bit more complicated. It says if I have two strings, S1 and S2, and two regular expressions, RE1 and RE2, and I have these two assumptions that S1 satisfies RE1 and S2 satisfies RE2, then I can say S1 concatenated with S2 satisfies app of RE1 and RE2. So this is again just a rule. And then for union, we have actually two rules. So we call them the left union rule and the right union rule. So the left union rule says that if the string S1 satisfies RE1, then S1 also satisfies the union of RE1 and RE2. So it also satisfies RE1 union RE2. The union right rule says that if S2 satisfies RE2, it satisfies RE1 union RE2. For star, we also have two rules. The first rule just says that the empty string satisfies anything that has a star. So it satisfies star of any regular expression RE. And the second rule says that if I have S1 that satisfies RE and S2 that satisfies star of RE, then S1 concatenated with S2 satisfies star of RE. If this is hard for you by any chance, just read the Wikipedia article about regular expressions. These are just the rules that define regular expressions. So you can think of this as some sort of operational semantics or rule-based semantics for regular expressions. This is what we're doing. We're defining semantics in Coq. Remember that in the last session, we actually started creating a programming language. We wanted to create our while programming language in Coq. And we already defined two things. We defined arithmetic expressions and Boolean expressions. And we defined a function that would evaluate them. Now, previously I said that the evaluation is a function, right? So I had a function that took an arithmetic expression and gave me a number. Intuitively, that's the same as what we used to call denotational semantics in our theoretical lectures, right? But we can also have rule-based or operational semantics. So how can I define rule-based semantics for my arithmetic expressions? Again, this is basically the same rules that we've seen in the very first lecture of this course. Here's what I'm going to do. I'm going to define an inductive proposition that takes two things. It takes an arithmetic expression and a natural number, and basically tells me if that arithmetic expression evaluates to that natural number. Okay, so this is no longer just a function that maps every arithmetic expression to a natural number. It's actually a relation that says, is this arithmetic expression in the evaluation relation with this particular natural number? And again, I'm going to have rules for this, and every rule is going to have a name. Now, the first rule is that if my arithmetic expression is of this format, and I hope you remember the definition of our arithmetic expressions, this was just a number, so it evaluates to the same number. The second rule says that if E1 evaluates to N1 and E2 evaluates to N2, then this arithmetic expression, which was like plus of E1 and E2, evaluates to N1 plus N. Remember when I was writing these rules and I was actually using this semantics notation where I was putting curly braces, well, not curly braces, double braces to show the semantics. This is basically the same thing. So this is just saying that the semantics of E1 plus E2 is the semantics of E1 plus the semantics of E2. It's just that we're giving it a name. I'm saying if the semantics of E1 is N1 and the semantics of E2 is N2. But anyway, from Koch's point of view, this is just an inductive proposition. It says that if E1 is in this relation with N1 and E2 is in this relation with N2, then this expression is in the same relation with N1 plus N2. Okay. And I can do the same things basically for minus and for multiplication. It's exactly the same. I'm not going to repeat it. Now, here's another way of writing it. And again, this is the difference between the two styles that I told you. So, for example, for A plus, I can write my conditions like this. I can say if this, then like this implies that, and that implies that. But I can also add my hypothesis like this. So I can have a rule that says if E1 evaluates to N1 and E2 evaluates to N2, then A plus of E1, E2 evaluates to N1 plus N2. That's it. Okay. Now, of course, I would also like to define some notation. I define this notation for evaluation. So I use this long arrow to say that some expression E evaluates to some number N. Okay. Nice. But now I want to actually show you how to define this with reserving the notation first. So I did this inside a module so that I can now do it again outside of the module. So here's the way I'm going to do it. I'm just going to say, let's reserve this notation. And then I'm going to define an inductive relation, which says when a particular expression evaluates to a particular natural number. And again, I have rules here. This is rule-based. But you see, I can now use that notation, so it looks much nicer. So I can say that this expression evaluates to N. Then my other rule is that if E1 evaluates to N1 and E2 evaluates to N2, then this expression evaluates to N1 plus N2 and so on. So the rules are the same. It's just that I'm writing them in a much nicer way. Okay. But we can also prove that our two definitions are basically the same. So I have two types of semantics. This is the same as the proof that I gave you that denotational and operational semantics are the same, right? So now it's just for arithmetic expressions. For arithmetic expressions, I have two different things. I have this relation which says whether A evaluates to N, and I also have this function A eval which takes A and gives me the value N. So I want to prove that they do the same thing. I want to prove that for all A and N, A evaluates to N if and only if, so another way of reading this is that the relationship evaluation says that A and N are in a relationship if and only if the function semantics says that the evaluation of A is N. Okay, so I'm just showing that the two semantics are the same. Okay, the proof, it's boring. I'm just going to go over it. It's casework. It's just casework and induction. At this point, you can do this easily. The point was not to actually show the proof. The point was to show you that these two are the same. So we now have two equivalent semantics. Okay, and there's actually a shorter way of doing it as well. This is a shorter proof. Again, go over this on your own. But now the next thing that I want to ask is what happens if I add division? Okay, yes. So I'm now creating again a new module, and I'm giving an extended definition for my arithmetic expressions. And I'm saying you can have a number, you can have plus, minus, but you can also have both multiplication and division. And you can just assume that this is division of natural numbers. Now, a problem that I have, if I want to define denotational semantics, if I want to just define a function that evaluates an expression, is that what happens if the expression has division by 0? If it has division by 0, then I don't have a value, but we've seen that the functions should always return something, right? So actually, I have to now say that the evaluation of an arithmetic expression is no longer a natural number, it's an option on natural numbers. So it can be none, okay? And I just want to show you how painful this is. So first of all, let's say that I want to define division with remainder. So I take A and B, I want to divide A by B, and so I have to return the quotient and the remainder. So the return type is going to be nat times nat. It's a pair of natural numbers, the quotient and the remainder. But the problem is that B might be 0, so I have to take an option on nat times nat as my return type. And you're already feeling that this is going to be painful. So first I do a pattern match on B and I say if B is 0, I cannot divide by 0, so I'm going to return none. Otherwise, if B is not 0, then I do a pattern match on A. And I say if A is 0, then return 0, 0. So the quotient and the remainder are both 0. But I have to return an option, so I have to return some 0, 0. And if A is A prime plus 1, then apply the same function recursively on A prime and B. This is very inefficient, but I don't care about efficiency. I just care that the function works. And if it returns none, I mean, at this point, it's impossible, but in your pattern matchings, you have to be exhaustive. So if it returns none, I also return none. Otherwise, A prime over B returns CD. So this means that A prime was C times B plus D. So now I have to do a casework. I have to say, if this D was B minus 1, then I have to return C plus 1 and 0. So if the remainder of dividing A minus 1 by B was B minus 1, then the remainder of dividing A by B is going to be 0. And the quotient is going to be 1 larger than what it was for A minus 1. Otherwise, the quotient remains the same, C, and the remainder increases. Okay.
I already feel that it is super inefficient.
Yeah, well, of course it's inefficient, but we only care about definitions here. We don't really care about computing with this. But now I have this division with remainder. If I want to just do natural division without remainder, that's also easy. So here I have to return an option nat. And all I do is that I just call the previous function. And if it returns none, I return none. If it returns some quotient and some remainder, I just discard the remainder and return the quotient. Okay. But now I have a bigger problem. And my problem is that I want to write a function that takes an arithmetic expression and evaluates it. But it might be that there is no evaluation. It might be that this function has to return none. So I have to actually define a bunch of operations on options. I have to define addition and multiplication and all of those things on options because they're not defined. So I have to define something like opt-add, which says that if A and B are two options on natural numbers, and if any of them is none, you return none. If both of them are something, you just take some of these two somethings, right? And then the same thing for subtraction, the same thing for multiplication, and the same thing for division. And in case of division, I need that function that I wrote before, natdiv. Okay, And finally, based on this, I can define a recursive function that evaluates an expression. So I can say, given some expression, arithmetic expression A, this function returns an option on that. And this is again casework. So if it's this, you just return sum n. If it's A plus of A1 and A2, you add. If it's A minus, you subtract. But these are all the opt, add, opt, sub, and so on that we defined here. So as you saw, if we add division, this type of semantics becomes much harder. How about the second type? How about the relation type of semantics or the rule-based semantics? That's actually quite easy. I will change it only a little bit. So again, I reserve notation and everything. This is the inductive relationship that I had before. Okay. And forget about all the other parts. This is the only part that is new. So I had rules for numbers, plus, minus, and multiplication. I'm going to keep all of those rules. I just need to add a new rule for division. Now, what is the rule for division? Very easy. If A1 evaluates to N1 and A2 evaluates to N2, and N2 is greater than 0, you see in my rule, I can just add the hypothesis that N2 is greater than 0. So I'm just adding this requirement to my rule. And if basically N2 times N3 plus N4 is equal to N1, and N4 is less than N2, so N4 is the remainder, then ADIF of A1, A2 evaluates to N3. So you see, it's a very simple rule. Of course, it's more complicated than the previous rules, but doing this is much easier than working with options. Okay. Let's do something else. Let's say that I want to have non-determinism in my expressions. So let's say I want to have this kind of arithmetic expression where I can also have something called any. And any is just some non-deterministic expression that can evaluate to any natural number. Okay. And you can think of it, I mean, later on, if I want to use something like this in my programming language, it might be that I have a value that is read from the user. So there's some input going on, and I don't know what the user will give as that value. So the only thing that I can assume about it is that it's just anything. So I have a new constructor, any. And now the problem here is that any can evaluate to anything. So if I want to use a function to evaluate my arithmetic expressions, this doesn't work anymore. Right? It's not, because there is no longer just one evaluation of any. I have infinitely many evaluations of any. But again, if I use the rule-based semantics, I can define this inductive proposition, and I just need one new rule. And all this says is that if n is a natural number, so for any natural number n, any evaluates to n. That's it. And everything else remains the same. So you see, this rule-based semantics is also easier when it comes to non-determinism. And of course, this was something that we saw when we were talking about semantics without Coq as well. It's actually quite funny how the last sessions of this course are very similar to its first sessions. Okay. But let's actually get into our programming language and let's actually define something. So until now, all of our arithmetic and Boolean expressions were without variables, right? So if you look at my definition of arithmetic expression, I mean, I added some non-determinism here, but in general, it's either a natural number or you just do the basic arithmetic operations. But of course, in a programming language, we are interested in expressions that have variables in them. And again, if you remember the beginning of this course, we had this definition of a state or a valuation which was like a function that mapped every variable to a value. So let's define something like that. I'm going to start a new module here, and I'm just going to import everything that I need. So I need some arithmetic, Booleans, strings, lists, and so on. Okay. Now, the first thing I'm going to do is that I'm going to define a mapping, because I want to say that my state is a mapping from variables to values. And I'm going to assume that all of my variables take natural numbers as their values. Okay. So here's what I do. I say that whenever I write total map of A, and A is a type, what I mean is just a function that takes strings and gives me something of that type. And the idea is that the string is going to be my variable name, and then the value of type A is going to be the value of the variable. Okay. So total map, whenever you see total map, okay, this definition just says that whenever you see total map, this is what it means. Okay. Now I'm going to define an empty map. So given an implicit type A and some default value, an empty map is just a total map that is defined by this lambda expression. So, and this lambda expression says that no matter what you get, you just return the default value. Okay. So I'm using functions to define my map, and this is a function that maps everything to the default value. And I see this as the empty state. Okay. So actually, I'm going to use variables that have natural values, and initially I'm going to assume that all variables have a value of 0. So my default value is going to be 0 later on. Okay. Now I also define another function called tupdate, which takes a map, and it also takes a string and a value, and just updates it so that the string is mapped to that value. So I'm adding one entry into my map. But this is a higher order function, because remember this total map A. So if I write it like this, it's the same as saying string to A. Okay. So this M here, this is a function that maps strings to elements of type A. And of course, I'm writing it just as total map A, but actually it's a function. So my tupdate is a higher order function that is taking a function as its parameter. Okay, now what should I do? I should also return a function, because I have to return the updated map. Okay, so what is the function that I have to return? And this is the definition of the function that I'm going to return. I write it with a lambda expression. I say that it's a function that maps x prime to this. If x prime is equal to x, EQB is a checks equality and gives you Boolean. If x prime is equal to x, then return v. Otherwise, return whatever the original map returned for x prime. Okay. So this is now a new kind of map, because the maps that we saw before were actually using lists, but now I'm using functions as my maps. Okay. Great. Now I can also define some notation. So I define this notation to mean that in the map M, I'm now mapping x to v. And I say that if I don't give you the M, it means that you start with the empty map with the default value 0, and then you do the same thing. So this is just definition of notation. Okay. Finally, I can define what a state of my program is. A state of my program is just total map nat, right? So every state is just a map that maps strings to natural numbers. That's it. That's what I'm saying here. I'm just assuming that all of my variables take natural values.
Yeah, I'm saying, why not type of?
You can have many different types. It's just easier to use natural numbers.
What's the intention? Do we do some arithmetic between the states? Why we need natural number to define state?
Look, because we want to have variables, right? So I'm saying a state is a function that maps variables to natural numbers. I'm just assuming that all of my variables are of type nat. All the values that my variables can take.
Okay, so it's kind of evaluation. Like we have some
Yes.
state, so it won't evaluate the state. Okay.
Yeah.
So we can define the entire value space in this one way.
Yes. So I'm just assuming that my small programming language, my while programming language that I want to eventually define, I'm assuming that it only has nat variables, basically. Okay. Great. Now I can define my arithmetic expressions, and this is again the same as before. I just added this. I say that an arithmetic expression can also be a variable x, and I use strings for my variables because every variable has a name, and I can just use the name of the variable, which is a string. Okay, so this is now the definition of my arithmetic expressions. They can either just be a natural number or one of my variables, or obtained by doing plus, minus, or multiplication on two other arithmetic expressions. Okay, now I can also define my Boolean expressions. This is the same as before. It's just that it's using the new definition of arithmetic expression, right? So I can have variables in my Boolean expressions as well. Okay. Now, this is the part where I'm going to define some notation. And again, look at the Coq manual for how notation works. But basically, what I'm doing here is that I'm saying, if ever I give you a string, and I'm giving you a string, but you expect to have an arithmetic expression, what that means is that you have to apply this constructor. You have to automatically convert this string to this constructor. Okay, and whenever I just give you a natural number, you have to apply this constructor. So that's what coercion means. Okay, and then I'm going to define a new scope, basically, and I'm going to call it com scope. Com stands for command, because I want to write my while programming language commands in a new scope. So that if I write, for example, plus, I know whether it's the plus in my while programming language or the plus in Coq, for let's say natural numbers. Okay, so I define a new scope. I call it com scope, and what I say is that everything that looks like this is in com scope. So whenever I want to write programs in my while programming language, I'm going to use this angle and then open curly bracket, and then I'm going to end it with closed curly bracket and closed angle. Okay, this is what this line says. And then the rest of it is just notation for everything that I have in my programming language until this point. So what do I have? I have, for example, arithmetic expressions. I don't like to write a plus, a minus, a multi. I just want to write plus, minus, and like star. And here I have Boolean expressions. I don't like to constantly write it like this, be true, be false, be EQ, so on. So I define notation for all of them. Okay. And this is why I said you should just use the file that I have there, because I don't want to go over all of these. And this is, you've seen this before. It's just defining notation so that I can write stuff more easily. And also, because I don't like to constantly write my strings like this, I'm going to define 4 variables, W, X, Y, and Z, and each one of them is just the string corresponding to it so that I can use it. Okay, now with all of these definitions and notations out of the way, I can actually write my arithmetic expressions like this now. So I can say, for example, 3 plus X times 2. So X is a variable, it's actually the string X, right? And this whole thing is going to be an arithmetic expression. And Coq knows that this is an arithmetic expression because I put it in between these open and close signs. So I'm telling it that this is in this new scope that I defined. So this is part of my while program, let's say. And I do this, and as you see, it can also understand the type. It says that this is of type arithmetic expression. Okay, now using this notation, if I want to write my evaluation function, it looks so much better. But the thing is that my evaluation function used to just take an arithmetic expression. Now it's different. It's going to take a state, which basically tells me what the value is for each one of the variables, and an arithmetic expression. And then it's going to evaluate it, because unless I have the values of my variables, I cannot evaluate, right? Okay, so here's how the evaluation works. I just do pattern matching. I say that if it's just a number, return that number. If it's just a variable, see what is the value of that variable in the current state. Remember, my state is a function that maps variables to values. And if my expression is A1 plus A2, evaluate A1 in the current state and evaluate A2 in the current state and just take the sum. And the same thing for minus and multiplication. Okay.
What's the difference between a reserved notation and normal notation?
Yeah, so reserve notation, the idea was that I haven't yet defined what I want to use for it.
Yeah, it's in there.
So yeah, this is what I'm doing. I'm saying I haven't given you the definition of this yet, but just reserve this as a notation and know that the definition is going to come. Okay, and then when I actually give the definition, I can use this recursively in itself. So it makes it easier to write recursive definitions for something that is also a notation. Okay. And then I can also write a function for evaluating Boolean expressions. So if I evaluate an arithmetic expression, I have to return a natural number. If I evaluate a Boolean expression, I have to return a Boolean. And by the way, I no longer have division, so I don't have to care about division by 0. Okay, so these are the, this is the way that the function beval is defined for evaluating Boolean expressions. So again, it takes a state of my program, and it takes a Boolean expression b. Now it says, if the Boolean expression is true, then return true. Very important, these two things are not the same. This one is a Boolean expression. They have different types. This one is just a bool. So this is BEXPR, this is of type bool. And then similarly, I say that if the Boolean expression is false, return the Boolean value false. If the Boolean expression is A1 equals to A2, and A1 and A2 are of course arithmetic expressions, just evaluate A1 and evaluate A2, and then use equals question mark, which was the function that checked if the two are equal and returned the bool. Now this one is for not equal, I just use the negation. This is Boolean negation to do that. This is less than equal, this is greater than, this is not. So for if it's not of B1, B1 is itself a Boolean expression. So I first evaluate B1 in the current state, and then I negate the evaluation. And also for B1 and B2, I evaluate each one of them. Again, very important that I evaluate in the same state. And then I take the Boolean answer. We defined a map or a total map to just basically be a function that maps strings to objects of type A. And we said that we use the strings, the names of the variables, to basically represent the variables in our while programming language. And this was the definition of the empty map. We have some default value, and this is just a function that maps everything to that default value. And then we defined the update. which takes a map. So this map is itself another function. So t update is actually a higher order function. Takes this map, it also takes a string x and some value v, and basically gives us the map that is obtained by mapping x to v in M. And this is how we obtain the function. We say that it's a function that takes any x prime, and if x prime is equal to x, then it returns v. Otherwise, it returns whatever M returns for x prime. We also defined these small concepts of notation. And then we said that the state is just going to be a total map of NAT. So it's a map that maps strings, variables, to natural values. And we defined our arithmetic expressions. The only difference here was that we now can have variables in there. We also defined our Boolean expressions. This definition was the same as before. It's just that it's using the new definition of arithmetic expression inside it. And then we defined some notation. I'm going to go over this really fast. And we defined some variables, x, y, z, and w. And we said that we basically write our programs in the while language inside these kinds of containers. Okay. So we saw the function for evaluating arithmetic expressions. And I can use my syntactic sugar here. So this was quite easy. We also saw the function for evaluating Boolean expressions. Now, at the end of the previous session, I finally talked about getting into the while programming language and actually defining the commands or the statements in this language. So again, if you remember from the very beginning of this course, I want to have a programming language where a command C can be one of these forms. It can either be just a skip, which doesn't do anything, or an assignment, or the sequential composition of two other commands, or a branching, which says if B, then do this, otherwise do this one, or a while. Okay. So this is how I'm going to define my command type. I'm going to say I define a new type called com for command. And it's either skip, and I'm putting capital C here so that I make sure I don't have any clashes with the constructors for any other type. So it's either skip or it's an assignment. And if it's an assignment, it needs two parameters. It needs the left-hand side, which is going to be a variable x. And we said that we show our variables by strings. And it's going to have a right-hand side, which is an arithmetic expression A. The other case is that it's a sequential composition of two commands, C1 and C2, or it's an if. And if it's an if, then you need a guard for the if, the Boolean expression that's the if checks. And then you need two commands, one for the then part and one for the else part. So C1 is the then part, C2 is the else part. And we also have a constructor for while. Again, while has a condition, which is a Boolean expression, and then it has a body, and the body of the while is just going to be a command. So this is how we define it. And again, now that we have defined our commands, we can go back and define notation. So I can say that if I write skip, I mean C skip. If I write this, I actually mean C assign. If I write this, I mean C sequence, and so on. So again, this is not really interesting. I'm going to go over it really fast. But now with this, I can actually finally write programs in the while language. So here's a simple program in the while language, and you know it's in the while language because it starts with angle bracket and ends with bracket angle. And this program is basically a program that computes the factorial of a number, right? So I start with y being 1 and z being equal to x. And I say, as long as z is not 0, multiply y by z and reduce z by 1. Okay? So it computes the factorial of x. And I can just define it like that. And with my notation and everything, it works. And then I can print it. And you can see here that Coq also does the type checking and says that the type is command com. Now, talking about this type checking, Coq is actually very smart. So based on the operators that we're using, it can find the type of any expression that you write. So for example, let's say I define this expression. It's just 1 plus 2. What is the type of this expression? If I print it, it's an arithmetic expression, so it's AXP. Whereas if I have something like this, true and not or equal to 4, this is a Boolean expression. So if I print it, it says that the type is BXP. And finally, this one, this is, as you see, actually an assignment. So it's a command. So if I print it, it says that the type is a command. It's a com. Okay. And the nicest thing here is that I can actually mix and match my programs. So I can do something like this. I write one program called subtract slowly. Okay, or actually, no, I'm calling it subtract slowly body. And what it does is it takes two variables, z and x, and decreases both of them. Okay. And then I can define something else called subtract slowly. And I can use the previous program inside this. So I can say while x is not 0, do the body. So decrease x and decrease z every time. And this is perfectly valid. It works. There's nothing wrong with it. And then I can actually apply it to some initial values. So if I want to subtract 3 from 5 slowly, I can do this. I can say x equals 3. So this is an assignment. This is the sequential operator. This is another assignment, sequential operator. And then I say just to subtract slowly. Okay. Here's an example of an infinite loop. So it's just while true, do skip. I can, of course, define it. We've seen before that we cannot have non-terminating functions in Coq, but this is not in Coq. This is in our programming language, in our while programming language. Okay. But one thing that this shows for sure is that I cannot have a function that just runs programs that I write in the while programming language, because every function in Coq has to terminate. And here I can write a non-terminating program in my while language. So I cannot have just a function in Coq which evaluates my entire program. And this actually takes us to semantics. So let's say that I want to define semantics here. Again, let's start with denotational semantics. And remember, the whole idea of denotational semantics was that you have a function, right? So I have a function, and it takes the initial state of the program. It takes the program itself, which is C, and it returns the final state of the program. Okay. Now, let's just go over every case. So we just do a match on C, and we check what kind of command C is. If C is a skip, I just return my initial state, because skip doesn't do anything, and my final state would be just my initial state. If the command is an assignment of this form, I have to actually do an update, right? So I have to take my state st, and I have to update the value of x to whatever the value of a is going to be at this state. So I first evaluate a at this state, at my current state, and then I say update the state so that x is mapped to the result of that evaluation. Okay. The next case is sequential composition. So if my program is of the form C1 sequentially composed with C2, C1 semicolon C2, here's what I can do. Actually, I haven't used let statements before, but that's actually quite easy. So I'm basically defining some variable. I'm saying let st prime be the result of evaluating st on C1. Sorry, evaluating C1 on st. So I'm starting with the state ST, and I'm running the first half of my program C1. And I say, let's say that takes the state ST prime. Now just run the second half C2 from this state ST prime and return that. Okay. The other case is actually quite easy because the syntax is a little bit hard to read. This is because our while syntax and the Coq syntax are quite similar. So this part is what's in the while programming language. I'm saying that if my program is of this form, if B then C1 else C2, okay, what should you do? You should evaluate B at the current state, and then you do literally an if. You check, does B hold at the current state? And this is Coq's if. And if it does, then you evaluate C1 at the current state. Otherwise, you evaluate C2 at the current state. Yeah. Now we have a problem with the while. Yeah, so I don't know what to do for while. So when we were defining our denotational semantics, we said that the semantics of a while can be defined by a fixed point of a particular functor. But can I define it here? Now, can I somehow use maybe a fixed point function in Coq to define this? And the answer is no. There is no way I can define it. And the reason goes back to this example. Right? So there are cases where I have programs in my while programming language that never terminate. But any function that I write in Coq should terminate and it should return something. So there is no way I can write something for while here. So I just say, I mean, it's already in the name of the function. It only works when you don't have a while. If you do have a while, I just return the same state and ignore it. Okay. But anyway, for programs that don't have a while, this is kind of useful. So here's a very simple evaluation. So let's say I want to set my initial state with two variables, where z is 4 and x is 2. Again, remember this was our notation for adding stuff to maps. Okay, so if I print my initial state, it says z is 4 and x is 2. Okay, now I consider a particular program. I'm going to call it add subtract, and this is what it does. It sets z to be z minus x, and then it increases x by 1. And it doesn't have a while loop, of course. Okay. So what can I do with this? I can apply this program to that initial state. And if I do that, then z should become 2 and x should become 3. Okay. So I say let result be basically the result of calling that function, this evaluation function, on the initial state and the program add subtract. Okay, I do this. Now, what is result? What's the type of result? It's itself a state. So I can say, okay, and again, remember that a state is a function that maps variables to values. So I can use result as a function. I can say, what is result of z? So what is the value of z when this program terminated? And of course, it gives me 2, and that's a natural number. What is the result of x? That's 3. Nice and easy. Okay, so this is a little bit of denotational semantic. Yeah, as we saw, we can't really have just a function in Coq that has the role of a, let's say, universal Turing machine, because when you've seen Turing machines, you've seen that there are Turing machines that can take the specification of another Turing machine and simulate it. I cannot have that here. I cannot have a function in Coq which takes a program in my while programming language and simulates it, because there are programs in my while language that don't terminate. Okay. Now let's do a little bit of operational semantics. So operational semantics is doable if you think about it. The idea in operational semantics was that we take one step at a time. So I can have a Coq function that just does one step of the execution. That's doable, right? Because one step always terminates. But let's actually see how I can do operational semantics. So I'm going to again define notation, and this is my notation. If I write st, and then I write a piece of code in between, and then I write another state st prime, what that means is that if I start at the state st and run this code, I will reach the state st prime. Okay, that's it. So I'm basically defining big step operational semantics here, not just small step. You can define small step with functions, but I want to define big step operational semantics. And okay, so we can't do it with functions for the same reason as before, because I have programs in my while language that don't terminate, but I can define inductive propositions. So these are, again, exactly the same as our proof rules. If you go back and watch my lecture on YouTube and see what I was telling you when I was teaching big step operational semantics, you see that these are exactly the same rules. Okay. So what kind of inductive proposition is this? What are the parameters? Where it takes a command and it takes two states. And basically the idea is, can this command take me from this state to that state? Okay. Rule 1, this is the rule for skip. I serve for all statements, for all states st. From st, I can go to st by running skip. And by the way, all of this is notation, this and this. This is just the notation that I defined here. But you see that it's now so much easier to read. So if I start at st, run skip, I end up at st. If I have an assignment, so I'm going to say for every state st, for every arithmetic expression a, and for every n and x, n is a natural number and x is actually a variable, a string. Okay. I'm going to say that if in the current state, the arithmetic expression a evaluates to the value n, then from the current state, I can run this program, the program that assigns a to x. And where will I end up? I will end up at the same state, except that the value of x is now n. And again, all of this is notation. Just see how many pieces of syntactic sugar we're using here. Okay. Sequential composition. The rule for sequential composition was also very easy. It was like, if you start at st and take c1 and get to st prime, and if from this second state, st prime, you take c2 and you get to st double prime, you can start at the initial state, take c1 sequentially composed with c2 and get to the end state. Okay? So again, these are just our proof rules. We're writing them in Coq syntax. That's the only difference. We're not doing anything new here. Okay. What about the rules for if? So if you remember, again, in our operational semantics, we had two rules for if. We had a rule for the case where if was true and a rule for the case where if was false, the guard of the if. So this is exactly what I'm doing here. I have a rule called if true, and it says that if the guard of my if b, when I evaluate it at the current state, gives me true, and if from the current state I run c1 and I get to st prime, then from the current state, if I run this entire program, if b then c1 else c2 end, I will get to st prime. Now I have another rule which is for the false case, and this is basically the same. It just says that my program is the same, but if the b, the guard of the if, evaluates to false at the current state, then I basically do whatever the else part does. If C2 takes me from ST to ST prime, then this entire program is also going to take me from ST to ST prime. And finally, for while, I also have two rules. So one case is the case where while is false. That's easy. If while is false, I basically don't do anything. I don't have any iterations. So I want to have a rule that says from ST running this, I end up at ST. When does that happen? When B does not hold, when the result of evaluation of B at the current state is false. Okay. The hardest case is the while rule when the condition is actually satisfied. Okay, so let's see what it says. It says, suppose the condition B is satisfied in the current state. And suppose that if I run one iteration of the loop, if I just run the loop body once, I go from the current state to this next state, ST prime. And suppose that if from ST prime I run the entire while again, I will end up at ST double prime. Then from ST, if I run the entire while, I will also end up at ST double prime. So this is loop unrolling. It's like unrolling just one iteration of the loop. And that's it. Yeah, and I see you tomorrow. I told you this is going to be a very short lecture because we covered everything in the previous lecture. Okay, at this point, we already know how to define our programs from the while language in Coq. We have a way of evaluating expressions. We basically have rules for our execution. We have rules for our operational semantics. So we can use these rules in proofs and theorems. So I can have a theorem that says a particular program terminates. And then I can use these rules to prove it. Yeah.
I think it sounds easy.
But using these things for proofs is going to be the topic of tomorrow. And we're also going to see how to add Hoare logic